All right, so I'm going to look at vector equations of lines. So this is lecture 25 of specialist maths. And we're really getting deep into defining lines using vector equations. So something to look forward to. Some prior knowledge, introduction to vectors, which was lecture 19, resolving vectors into their rectangular components, which we spoke about in lecture 20, and then the dot product between vectors, which was lecture 22. So you're going to need to know those ideas that were covered in that in order for vector equations to make sense. And then, so the key concepts we'll cover in this are vector equation of lines. So you can do that in two ways. So through what's called a point and a direction. If you get given a point in some direction, then you can define a vector equation of a line. Or if you get given 2 points, you can define a vector equation. And then we'll look at converting vector equations to Cartesian form or Cartesian equations, and looking at the reverse of that as well, going from Cartesian to vector in both 2 and 3 dimensions. And then we'll summarize the different ways that we can represent lines in 3 dimensions. Then we'll look at parallel and perpendicular lines, and then we'll look at finding a distance from a point to a line. Okay, let's jump into it. Let's start by looking at the vector equation of a line. Now, I have made another video about this, but I'll just recap it here because it's important to go through. So, okay, so a vector equation is just this idea that you have a vector pointing in space. And if that vector traces out a path, you can describe the line that it traces out. So let's jump into it. Let's just try and read this for a moment. So we've got some line L, which is the set of all points P, and all those points P can be described by a vector from the origin to some point P, that is equal to some vector A plus some multiple of some other vector D. And that scalar multiple is this parameter T, where T is just some real number. So a little bit confusing. Generally, you won't see this set notation. You'll just see this vector notation. Remember, when it's bolded, it means it's a vector. So we'd say that R of T is equal to A plus TD. And let's just sort of make some sense of it. If we've got some vector OA, so this is this vector OA, which is vector A, which is this sort of lowercase bolded A, is the same as this vector here. And then we've got some direction. So we've got that sort of vector A pointing in some direction, pointing at some point, and then you've got this vector D that tells you the direction in which that sort of point is moving. So in this case, so just for an example, this red vector is sort of the direction we're moving. And then we can have multiples of that, right? So the actual point P is over here. So if we take vector A plus some multiple of D, we scale this direction vector D up, it gets us to this point P. And you can see O to P is this vector equation. A plus vector D multiplied by some scalar T is the vector OP, which is also R of T, which is defined as vector A plus T groups of vector D. So yeah, that's what you get. And you can see, let me just get rid of that for a moment. If we change T, we're either scaling that point up or down, right? We're scaling this part of it up or down. So you can see that point P actually traces out a line in space, right? And that's what we have shown here. If we put that on, we can see that that point P is tracing out that line in space. If you don't believe me, we can put that back and we can make this a trace, right? But I think you get the idea. So that's pretty nifty, I think. So that's that line there. So yeah, that is how you define a vector equation when you get given a point and a direction. Okay. Let's have a look at a different situation when you get given the vector equation of a line when you get given 2 points. Okay, so let's look at it. So let's imagine we get given 2 points. We get given some point A, and then again we have vector OA to that point A. Again, this is this vector A. And we've got some other point B, and no surprise that this is going to be vector OB, or lowercase bolded B. Okay, and then what we're going to say is, all right, what is the equation, the vector equation of the line that goes through the points A and B? So you can just imagine that you've got some line that would go through these points here like this. And what we're going to do is we're going to define the vector equation of that. Now, what that's going to look like is this. and just take my word for it for a moment that this is the vector equation of the line when you get given 2 points. R of t equals A plus t groups of B minus A. Okay, we don't want to take anything at face value in maths. We really want to understand why it's the case. Let's just investigate this B minus A part. So vector B minus A, if we do some vector subtraction, you'll realize that that's actually this vector here, which corresponds to the vector between here and here. Remember, the vectors, doesn't matter where they're positioned in space, as long as they have the same size and direction, then they're the same vector. So this vector B minus A would go from here to here. And that should make sense from some vector subtraction or vector addition, if you like. B minus A is the same as negative A plus B. So remember, when we do vector addition, we go negative A, so it'd be going in this direction, plus B, so it'd be starting here, going this way, negative A plus B, and then you connect the tail to the tip. So you can see why this vector B minus A is this one here, right? Okay, and so what we get is a situation where, yeah, this point P, we take vector A, and then we take a multiple, then we add on a multiple of vector B minus A. And so that gives you the point P. And so that point P will travel across this line. And then as you can see here, as we change the parameter T, we get this situation, right? And P is traveling along that line. Hopefully that makes some sense. Let's just put some values of T that are familiar so we can make some sense of it. If T is 0, then this whole second part of the vector equation goes to 0. So you just get vector A, and that should make sense. But other than that, you can see that we're taking vector A and we're adding a real multiple of vector B minus A. So that's just going to travel along here, because remember, B minus A points in this direction. And so if we take negative values of that, it's going to be the left of A, left of A. If we take positive values of T, it's going to be the right of A, because we're scaling up that B minus A vector in that direction. So that's how you can get the vector of equation of a line in when you get given 2 points. And obviously this down here is just for illustration purposes. But hopefully that makes some sense for how you find the vector equation of a line given 2 points. Okay, the fun continues. Let's have a look at the next thing. Let's see if we want to go from a vector equation to a Cartesian equation in 2 dimensions. So 2 dimensions is always a lot more friendly. So let's have a look. So let's imagine we get given some vector equation. So we get given some vector I. So remember, I is the component vector in the x direction, and plus 5j plus t groups of I plus 2j. Again, j is the unit vector in the y direction. Okay, so that's our vector we've got. We want to convert that to the equivalent Cartesian equation in 2 dimensions. So let's think about how we might do that. That is, I should just point out that when t is, let's just make t 0 for now, make things easier. This line here is this equation. When t is 0, you just get 1 across and 5 up. Hopefully that makes sense. 1 adding the unit vector in the x direction plus 5 groups of the unit vector in the y direction. So that would get you to the coordinate 1, 5. And then obviously this other stuff here, so we scale it up and down, changes those values, right? In any case, let's leave that there and think about how we can find out the equation that this point P traces out. See how it's tracing out a linear line? We want to know the equation of that line. So what we're going to do is going to expand things out a little bit. So expanding that T in, no rules against that. Just putting this Ti term over to the left just to group things. And then we just want to take I out as a factor. So you get 1 plus Ti plus 5 plus 2Tj. And then what we want to do is we want to say, all right, well, this is the x component, right? In Cartesian form, this corresponds to how much you're moving left and right. So we're going to say that x equals 1 plus t. So now we're doing the conversion to Cartesian equation, right? Okay, so therefore t equals x minus 1, just rearranging this. Okay, if t equals x minus 1, we also know that y in Cartesian form is 5 plus 2t. Or rather, y in vector equation form is 5 plus 2t. And then but we know that t is x minus 1. So we get y equals 5 plus 2 by x minus 1. And then just simplifying things, you get 2x plus 3. And no surprises, this pink line is the equation, y equals 2x plus 3. You can just sort of check that. You've got a y-intercept at 3 and an x-intercept at negative 1.5 or negative 3 on 2 if you rearrange that. So that does check out, and that point P obviously traces that point along there, right? So pretty nifty. And obviously if we put it to negative, no, when T is negative 2.5, you get an x-intercept, as it were, at negative 1.5. So yeah, that's how you find the vector equation to a Cartesian equation in 2 dimensions. What we might want to look at next is how we go the other way, I think. Yeah, so we want to go the other way now. So, okay, let's have a look if you get given an equation like this. So you get y equals 2x plus 2. Okay, we want to go the other way now. So we know that we're going to parameterize it. Okay, so what that means is we introduce a new parameter. So we're sort of doing the reverse of what we did before. So now we're going to say x equals t and y equals 2t plus 1, right? So essentially we just set x equal to t, so y, and then y equals 2t plus 2 rather. Okay, and then you're going to put it into vector form, right? So you're scaling up in the x direction by t, and you're scaling up in the y direction by 2t plus 2. Okay, and then so you get this. This is what you end up with if you just expand things and simplify a little bit. You get t multiplied by I plus 2j plus 2j. Okay, let's just break that down a little bit. This should feel intuitively correct because this 2j is a point. There's a point on the graph. We know just from linear relations that this is a y-intercept of 2. So 2j, when t is 0, this whole term will go away, right? So when t is 0, it should be pointing at a y-intercept, right? So we get that pointing at that y-intercept there. Okay, and this part here should make sense. This is the gradient. The gradient of this graph, again, linear relations is 2. So the rise over the run is 2. So the amount you go up in the y direction divided by the amount you go across in the x direction, rise over run should be equal to 2. So 2j divided by, 2 divided by 1 is the gradient, right? So this is important, and you need to hold on to this idea for things in 3 dimensions because essentially you take t multiplied by the vector equation that represents the gradient, and then you add on some other point, right? Now, yeah, another thing we could say about this is just this vector without the 2j would just be a parallel vector to y equals 2x plus 2, to the equation y equals 2x plus 2. So we're sort of just incorporating the gradient and a point into that. And then you can see that that vector points along that line 2x plus 2. Hopefully that makes some sense. Okay, alternatively, and this is where it's a bit interesting, we could do it another way, right? But we could parameterize it another way. And this is where we've got to be a little bit careful. You can see that if t is 0, I was just thinking to myself, all right, if t is 0, we could have the vector could just start at a different point, right? So for example, the gradient's the same, I plus 2j, but we can see now that the point I picked was different. I picked a different point. I picked negative 1 for when t is 0 here. So this is where we've got to be really careful, and I'm just trying to think to myself. So when we're going from a Cartesian to a vector equation, there can be multiple answers. Okay? These vector equations are different, but they both trace out the Cartesian equation 2x plus 2. And as you can see, that seems to be the case. The vector equations are different, just based on the point that I picked for what t starts at, for what the vector starts at when t is 0. But other than that, it still traces out the line 2x plus 2. So you have options, I suppose. In fact, I think there's infinitely many options when you make this parameterization to go from a Cartesian equation to a vector equation. Okay, so hopefully that's interesting. Yeah, let's look at the next thing where it gets a little bit more tricky. So let's do a similar thing in to go to Cartesian form in 3 dimensions. So a line through, so let's have a look at this example. So the line that goes through 2, 3, -1 and is parallel to this vector, A equals 4i minus 2j plus 5k, can be written like this. Okay, let's just break this down a little bit. So what it's saying is it needs to go through this point, 2, 3, negative 1, which is here. Now we're in three dimensions, right? So this is this point here, 2, 3, negative 1. And it has to be parallel to this vector, which is 4i minus 2j plus 5k. Okay, that's basically telling you the gradient, right? Because if it's parallel to that vector, then the gradient of this line and the line that we're, the vector equation that we're trying to come up with must be the same, just like in two dimensions, right? So what we end up with is this, just like we said before, we pick a point, so 2i plus 3j minus k, and this vector here, to sort of spoil the game a little bit, this pink vector is the answer, but when t is 0, it will point at that point, 2, 3, negative 1, right? Pointing at that blue point there, which is at 2, 3, negative 1. So, um, yeah, that's just this part if t is 0, but then we obviously can incorporate t to define the whole line. It needs to be parallel, so need to, again, it's going to be just this. It's going to be t groups of 4i minus 2j plus 5k. And then as we change t, it just traces out that whole point, traces out that line, and it goes to the point that we want it to. So the vector equation of a vector equation in three dimensions can be defined when you get given a point and a parallel vector. That's the two bits of information you need in order to define the vector equation in three dimensions. Okay, so that's yeah, and now what we want to do is if there's other ways we can describe it, right? So we can describe it using the parameterized form. So what that would be is, again, we just sort of rearrange this, expand the t in, collect the i's, the j's, and the k's, and take them out as factors, and then set the x component equal to the coefficient of I, the y component equal to the coefficient of j, and the coefficient of k equal to z. And so this is what we call the corresponding parametric equation. So x equals 2t, 2 plus 4t, y equals 3 minus 2t, and z equals negative 1 plus 5t. Okay, so that's what we call the parametric equation. So again, we've got two forms here. We've got the vector equation so far. Now we've got the parametric equation. And now we can, if we just rearrange this for t, just rearranging each of these for t, we get t equals x minus 2 on 4, t equals y minus 3 on negative 2, and t equals z plus 1 on 5. Okay, it might look a bit odd, but this is what's known as Cartesian form because we can't have a single equation to define a line in three-dimensional space like we can in two-dimensional space. So we end up with this, and I guarantee you if you go over to GeoGebra or Desmos or something, preferably GeoGebra, where you've got the 3D viewer and type this in, that will give you this line that's traced out by this pink vector. So let's just let that play so you can sort of see what's going on. And yeah, they're the three forms of that line. But yeah, hopefully that's making some sense. That is the vector equation to Cartesian form. Notice it doesn't say Cartesian equation because you can't define it with a single equation. You need multiple equations. Okay, so that's that. All right, almost there. One of the longer ones today. So let's just sort of summarize all of that information. So when we are talking about lines in three dimensions, it can be described with a vector equation, which we spoke about just there. So R equals A plus TD. Yeah, where A is some position vector to a point, just like we spoke about, and T is the direction vector or a vector parallel. So just to sort of drive this point home, that's what we spoke about back over here, right? When we had this, we said you get given some point and some direction. Okay, another way to think about this direction vector D is that it is you get given some vector that is parallel to the direction, right? Like this vector here is parallel to D, obviously, this blue vector underneath D. So, yeah, that's how we define the vector equation. Okay, the parametric equation is this. The parametric equation is just going to be the x coordinate is equal to a1 plus t groups of d1. Y is equal to a2 plus t groups of d2, and z is equal to a3 plus t groups of d3. And then similarly, just like we did before, I think the example's easier to look at. The Cartesian form would take this form. Okay. So let's just look at an example to make things easier. A line passing through the point 1, 2, negative 3 and parallel to this vector 3i minus 2j plus k. So the vector equation, again, we pick a point. When t is 0, let's put t to be 0, it's pointing at that point here, which is 1, 2, negative 3. Okay, 1, 2, negative 3. X coordinate of 1, y coordinate of 2, z coordinate of negative 3. All right, and then this here sort of incorporates the direction into it because this is parallel. The line we want has to be parallel to this vector. And so, yeah, we get this. That is what this line is. As t changes, we obviously trace out that line in space. You can see that point is traveling along that line. Okay, so I think that's pretty cool. And then if you want to do the equivalent parametric equation, yeah, it's just what we said here. 1 plus 3t. 2 minus 2t. Negative 3 plus 1t. So that gives you the parametric equation. Rearrange these for t, rearrange each one of these for t, and then you can write it in the Cartesian form. Okay? And then all of those are valid ways to represent the line in 3 dimensions. Vector equation, parametric equation, Cartesian form. Okay, almost there. 2 to go. Next one's going to get hectic. So hopefully you've got good color vision because we're going to need to distinguish between all these different colors here, which should be a bit of fun. Okay, so we're going to talk about parallel and perpendicular lines. So let's think about what that is. So for two lines L1, where L1 has the vector equation R1 equals A1 plus T groups of D1, and L2 is the same thing, but the parameter is S rather than T. The lines L1 and L2 are parallel if and only if D1 is parallel to D2. Okay, that should make sense. The direction vectors of your vector equations, the direction vector component of your vector equations need to be parallel. Otherwise, your vectors are not going to be parallel. Okay, and similarly, the lines L1 and L2 are perpendicular only if D1 and D2 are perpendicular. So we need them to be at right angles. Okay, so again, example will help. This is where we need to know the difference between the colors, all right? So let's talk through all of this and then I'll play the animation over here. So L1 is the orange line. So L1 equals, so line 1 is the direction vector R1, which is just T groups of 2i plus 3j plus 4k. And that's this one here, right? So when T is 0 on that orange line, it's tracing it out, so it's going to be a bit confusing. But when T is 0 on that orange line, then this whole thing goes to 0. So the orange vector has disappeared. It hasn't disappeared. It's the 0 vector, which must be at the origin, right? Okay, the purple line is these are just made up, obviously. R2 equals 1i minus j plus 2k plus S groups of 2i plus 3j plus 4k. All right. The key point here is notice that the direction components of these vector equations are parallel. This part is the direction component. This part is the direction component. They're the same, right? So the lines L1 and L2 are parallel because the direction vectors are parallel. So maybe I will play this now just so you can see. You just want to be looking at the orange one and the purple one. Ignore the pink one and the brown one for now. But yeah, if I play that, we're just looking at purple and orange. And lo and behold, they are parallel. Isn't that cool? So we end up with that situation because the direction vectors of those are parallel. Okay, let's have a look at, let's get rid of that so it's not as confusing. And let's look at perpendicular lines. So L3 is the brown vector equation. That's color there is brown, believe it or not, looks black. And yeah, so it has, again, just made up, but a vector equation 0i plus j minus 2k plus t groups of 2i minus j plus 2k. All right, what we're interested in is the lines being perpendicular. So if the lines are perpendicular, then their direction vectors must be perpendicular. And if something's perpendicular, we know from the dot product that the dot product between the two vectors must be equal to 0. So if we look here, the lines L3 and L4 are perpendicular because the direction vectors satisfy that when you take the dot product between them, you get 0. So 2i minus j plus 2k dotted with 2i plus 6j plus k does equal 0. Because remember, when you take the dot product, you multiply the coefficients of the respective components and then add them together. So let's do that. 2 times 2 is 4 plus -1 times 6. So that's 4 minus 6, which is -2, plus 2 times 1 is -2 plus 2, which is 0. So the scalar product or the dot product between these two vectors is 0. And so L1s and L3 and L4 are perpendicular because the direction vectors satisfy that the dot product is 0 between them. So if we again play that, now you want to be looking at the brown lines and the pink lines. And you'll notice that they're parallel. It's a bit glitchy because it's trying to do a lot. But once the pink ones, there we go. So you can see the brown line and the pink line are at right angles. It's a bit hard to see, but I think you can see that. They're at right angles here because the dot product between the direction vectors of the respective vector equations is 0. It's a mouthful. Okay, hopefully that makes some sense. But yeah, pretty cool diagram, I think. Cool to me anyway. Anyway, let's have a look at the last thing, which is another example. Okay, maybe just pause the video because it's getting pretty heavy at this stage and maybe read it, see if you can make some sense of it. But I will talk through it. So we're going to talk about a distance from a point to a line. So you get given some vector equation, say, or it could be in parametric form or Cartesian form, and you need to find the distance from some point, say the origin in this case, to that line and the shortest distance, right? So maybe a picture will help here to sort of help you think about what we're doing. Again, this black vector is just some vector in space. We want to know what is the distance from the origin to that line. And you're probably like, well, what do we mean by that? Well, what we mean is what's the shortest distance, right? There's obviously this distance here where the arrow is at the moment is not the shortest distance. I can tell you that where this pink dot is the shortest distance. And that's our job to find out what is the length of this vector essentially. And yes, maybe just some key ideas you need to know is that the shortest distance from some point to a line it has to be perpendicular, doesn't it? Because that's going to give us the shortest distance. So where this vector and this line are perpendicular is where you're going to have the shortest distance. So here's the actual problem. So find the distance of the line with this vector equation, 2 minus ti plus 3 plus 2tj plus 4 plus tk from the origin. Okay. And the solution. So the equation of the line can be written like this. Okay. So putting it in the form we're more familiar with, where we've sort of got this point, 2i plus 3j plus 4k, and a direction component. So it's t groups of -i plus 2j plus k. Let's just dwell on this for a second because it really is important to understand this. 2i plus 3j plus 4k. If t is 0, this part goes to 0. So when t is 0, let's put it to 0. Somewhere there. Then that point has an x coordinate of 2, if you can see that, as an x coordinate of 2, a y coordinate of 3. It's a bit hard to see that, but it is a y coordinate of 3, trust me. And a z component of 4, right? Is this part here. Okay, so the the direction vector is -i plus 2j plus k, must be parallel to that line. Okay, the required distance is the magnitude of OP dash, where P dash is the point on the line such that OP is perpendicular to the line. Okay, so what that means is that pink point is P dash. We want to know what is the distance to that point P dash. So we need to know the magnitude of the vector OP dash. Okay, we know that for any point P on the line, so any point, not necessarily there, the line OP, the vector OP equals the vector equation R of t, which is this. We know that, so what that's saying is the vector from O to any point P on the line must be just equal to the vector OP, which is the vector equation R of T. Okay. And then so what we want to do is we want to actually take the dot product between this vector OP and direction vector D. Because remember, the direction vector tells you, yeah, the direction we're moving. And so what we need is the vector OP and the direction vector to be perpendicular. Because if they're perpendicular, the dot product is zero. And then that's what you want. You want to know where it's perpendicular. So you take the dot product between OP and um, and the direction vector D. So you take this and dot it with its direction. It gives you this, and that gives you 7t plus 8. So you take the dot product. We need the dot product to be equal to 0. So we're setting 7t plus 8 equal to 0. So solving that for t gives you negative 8 on 7. Okay. So when t is negative 8 sevenths, we're going to take negative 8 sevenths, sub it into the vector equation. Why is that? Oh, yeah, sorry, yep. So subbing negative 8 sevenths into this vector equation. So it's 2 plus, because it's take away negative 8 sevenths, I plus 3 minus 2 groups of negative 8 sevenths. You get the idea, I hope. I'm just butchering it. But basically, we're taking negative 8 sevenths and we're substituting it in here for t, right? And then simplify, you get this 22 on 7i plus 5 on 7j plus 20 on 7k. Okay, so now we've got our vector that's pointing from the origin to the line and it's perpendicular to that line. So that must be the shortest distance. And then you've just got a vector that you need to find the magnitude of. And then to find the magnitude of a vector in 3 dimensions, you just apply Pythagoras in 3 dimensions. So you get this. And then you get an answer like this, 3 root 101 on 7. A lot of this you could use a calculator for, but I just want to show you that it's true. So what we said here, the sort of conclusion was that when t is negative 8 sevenths, our vector from the origin will be perpendicular to that line. So let's go to settings here, and let's change the slider to be negative 8 sevenths. Negative 8 divided by 7. And you notice there, it's pointing at that point. So there you go. When it's negative 8 sevenths, we get this. And if we have any luck, we might be able to find the distance of this. Nope, but bear with me. We just make a line segment between that point there and that point there, just so you know I'm not making up fibs. We should be able to find the distance or length of that. And we get 4.31. And I guarantee you, if you take that, 3 root 101 on 7, and put it in a calculator, you'll get 4.31. Don't believe me? Let's check. Desmos. Desmos is great just for quick calculations. Can I remember it? Probably not. 3 square root 101 on 7. 4.307, which rounds to 4.31. So we're on the money. Okay. Me explaining that probably wasn't that helpful, but pause the video and just read through it. Hopefully it makes some sense. Give us a thumbs up if you found this at all useful. Good luck with everything you're doing. As always, if you need any private tutoring, feel free to contact me and we can do some online tutoring and talk about some of these interesting ideas. So good luck with everything you're doing, and I'll talk to you soon. See you later.